So, we have looked at integer quantum Hall effect in great details. Almost everything that are relevant, we have done that. And if you remember that we had shown this picture that is there on your screen. So, this is the integer quantum Hall effect. So, this is, let us abbreviate it as IQHE, where you see all those plateaus. The left hand side is for the magnetoresistance and the right hand side is for the Hall resistance. So, even though it is not clear, you know what it means. So, this is a nu equal to 1 plateau, and then there are nu equal to 2 plateaus, nu equal to 3 plateaus, and so on. So, these are the resistivity plots, Hall resistivity plots, and along with that there are these peaks in the magnetoresistance behavior as a function of B, and you see that the B is pretty large here. I mean, it has been taken up to something like 14 or 15 Tesla. And we are very well aware that why do these plateaus arise in spite of the system being a dirty two-dimensional electron gas with no time reversal invariance or translational invariance. In fact, the time reversal invariance is the reason, or the loss of time reversal invariance is the reason for these plateaus to be quantized, and they are related to the Chern number, which is what we have seen. And we have also seen that it is a situation in which whenever these Hall plateaus jump from one new value to another new value, it jumps up or jumps down depending upon how you want to view it, the magnetoresistance that shows a peak there and so on. So, that is there for all the way to low values of magnetic field, excepting that at very low values you see that this region, you see that there is a linear behavior of the Hall resistance. So, linear behavior, and this linear behavior is related to the classical Hall effect that we have all seen either at the school level or young undergraduate level, where the Hall resistivity or the Hall coefficient is proportional to B linearly in B, and the slope gives you information about the density of the carriers and the type of carriers, that is whether it is a N type semiconductor or a P type semiconductor. Almost soon afterwards, people have found this FQHE, and in which the fractional plateaus are seen. I completely agree that these are not clear fractions, but one can actually see a fraction as 3.5, there is one at 3.7, there is one at 2.3, and there is one at 4.3, and so on. So, these are plateaus being seen at the fractional values, and that is why it is known as FQHE, or the fractional quantum Hall effect. And this forms the discussion for us for the next few lectures before we wind up the course. So, what are the reasons for these fractional plateaus? Does it mean that there are fractional feelings, or electron is divisible, where we know that these in terms of the Corbino disk picture, there are these the Hall effect or the Hall phenomena is perceived as Hall or the quantum pump, in which there is an electron that has been transferred from the inner edge of the disk to the outer edge, and the 2 electrons being transferred, 3 electrons being transferred, and that forms these plateau labels of the plateaus that we have indicated here as 1, 2, 3 and 4 and so on. So, if they are fractions, that is these labels are fractions, would it mean that the electrons are divisible? And certainly not. In fact, that is what we are going to talk about, that the electrons are not divisible, they are a fundamental, the electronic charge is a fundamental quantity. There is nothing called a third of an electronic charge and so on, but still we see plateaus at fractional values. So, we start this discussion on the fractional quantum Hall effect. And which we abbreviate as FQHE. Okay. So, to show you one more picture, these are probably a little more clear than the earlier one. So, you see that these are integer plateaus here, and let us show the fractional plateaus by a color. So, these are these fractional values 5 by 3, 4 by 3, 2 by 3, 3 by 5, 4 by 7, half, and so on and so forth. 2 by 5, 3 by 7, the mostly rational fraction and the proper fractions, which means that the denominator is larger than the numerator, but there are also improper fractions that are seen in experiments, as well as there are different kind of fractions that are noted in experiments, and overall about more than 80 such fractions have been noted overall in experiment. So, this is a single figure which shows both integer and fractional quantum Hall effects. Okay. So, in order to understand, we have to again understand that the energies of these electrons in a magnetic field, which we already know, but does anything change in this fractional quantum Hall effect? It turns out that nothing changes, excepting that these wave functions are found to have a radial symmetry, and in fact these are called as Laughlin states, which we will see, and or these Landau levels rather have radial symmetry, and these have to be worked out. So, what I am going to show is I am going to take a gauge that captures this radial symmetry, and this is called as a symmetric gauge, and in this gauge we shall do calculations and we will find out the degeneracy of the Landau levels and the wave functions that are relevant for the discussion. Okay. So, let us start with the gauge. So, we start with the symmetric gauge. And let me mention a priori that there is a lot of mathematics that is going to follow. They are mostly algebra and simple algebra, but they need to be done in order to understand what is the nature of the wave function and how we can write it in terms of particularly in terms of complex numbers like z, which is equal to x plus iy and so on. And before that, I urge the readers to have a look at the simple harmonic oscillator in spherical polar coordinates. Okay. So, you know that one dimensional oscillators have energy which is n plus half h cross omega. There is no degeneracy, but in 2D in Cartesian coordinates it has nx plus half plus ny plus half h cross omega. Omega is still given by this root over k by m, and now there is degeneracy there. Now, if you go to 3-dimensional spherical polar coordinate, if you solve the problem in 3-dimensional spherical polar coordinates, you will see the importance of the angular momentum operator, and the quantum number corresponding to the angular momentum quantum number is important to find out the degeneracy. You can look at any good quantum mechanics book. In particular, you can look at Cohen-Tanoji, which gives you a very nice introduction about this problem, that is simple harmonic oscillator in 3D spherical polar coordinates. Okay. And this actually would help you a lot in understanding this part, because we are still going to get these harmonic oscillator, these energies as well as the wave function. So, we start with the symmetric gauge. What I mean by symmetric gauge is that for constant magnetic field, which we know that in this particular case it is a constant. So, there is a 2-dimensional electron gas which is pierced by a uniform field in the z direction, and we write down the gauge as half r cross b. Okay. You see, if you remember that we have taken this a to be like minus y b x cap, or we have taken it as x b y cap and so on, okay, which are same, and this is called as a Landau gauge. And in this particular gauge, what came out is that after we have solved the problem, the energy levels came out as n plus half h cross omega, where n can take values as 0, 1, 2, etc. Now, depending on the gauge chosen of these two, that is it's minus y b x cap or x b y cap, there is either kx or ky they continue to be good quantum numbers, and any value of kx and its quantization would be acceptable for any given value of n. And that gives rise to an enormous degeneracy into the problem, that is, there are very large number of quantum states that are available for the electrons to occupy, which means that each Landau level is heavily occupied by electrons, or they are heavily degenerate. However, we are foregoing that constraint, that is, neither kx nor ky continue to be good quantum numbers, but instead we will see that the Lz or the Jz, that is the z component of the angular momentum quantum number. It is probably safer to talk about Jz, because where Lz and Jz would mean the same thing, because there is no spin involved. But we will talk about Jz. You have to keep in mind that if you look at another book, it might actually talk about Lz, but they would mean the same thing. All right. So, this is equal to half of minus by x cap plus a bx y cap. Okay. So, that is the form of the vector potential, and this choice of the gauge actually breaks the translational symmetry in both the x and the y directions, which means that kx and ky cease to be good or conserved quantities, so to say. Okay. And this will be very helpful for us to understand the fractional quantum Hall effect. So, we will find out the momentum, and the momentum, let us write it as the momentum which is p plus Ea. This momentum, let us call it as some momentum called as pi, and this is important to understand that this momentum is gauge invariant, but it is not a canonical momentum. What I mean by a canonical momentum is that x and x component of pi do not have these commutation relations which are IH cross. So, if they have, then they are called as canonical, but these can be shown as they do not obey the canonical relations, but nevertheless these are gauge invariant momentum. So, we use this just like what we have done it for the first course of quantum mechanics to study linear harmonic oscillators. We have used p and x combinations, linear combinations of p and x in order to write A and A dagger. Here we will do a different thing, but something similar, that is, we will write down these creation and annihilation operators, namely A and A dagger, to be so A dagger is creation and A is annihilation operator. So, these will be written in terms of the x component of pi and the y component of pi. So, what I mean by that is your A is equal to, so it is a pi divided by HEB, this is equal to pi x minus I pi y, and A dagger equal to pi divided by HEB and pi x plus I pi y. So, I hope the discussion that we had done so far is clear, and the rationale or the motivation is clear. The motivation is that we are going to talk about the fractional quantum Hall effect. But however, doing a full calculation leading to the conductivity is something that we will not do, rather because we have done that using the Kubo formula, and here there is a lot of numerical calculations involved in order to verify various things, such as the plateaus or this fractionally quantized plateaus and so on. So, we will not do that, rather we will concentrate more on the nature of the wave function, and that to the lowest Landau level, and various things, various properties related to the quantum Hall fluid. So, in order to do that, we have noted that the most suitable this gauge here is the symmetric gauge and not the Landau gauge that we have seen earlier. And in this symmetric gauge, we have do this problem, that is the problem of electrons in a magnetic field, and find out the energy eigenvalues. And in order to do that, we have written down some annihilation and creation operators in terms of these canonical momentum, non-canonical momentum, but gauge invariant momentum, which are pi x and pi y, the components of that. Okay. This is of course your A dagger commutation relation. You can easily find out. This is something that even though I expect you to do, let me do that, because we are introducing these things for the first time. So this is both get multiplied, the prefactors get multiplied, and we have a pi x minus I pi y and a pi x minus plus I pi y. Okay. So that's your A dagger and so on, and so there is a pi x plus I pi y and pi x minus I pi y. All right. So this is something that one has to calculate, and let us do that quickly. It's HEB, and so this is a pi x square plus I pi x pi y plus pi y square plus minus pi x square plus I pi x pi y and minus I pi y pi x and pi y square and so on. So if you simplify that a little, you get this A dagger as 2 pi I by EBH pi x pi y minus a pi y pi x. Now these are simple things you should be able to do, and this is nothing but this is I by EBH cross, and this is equal to pi x pi y commutator. So A and B they don't commute, of course, which we know, and the commutation is expressed in terms of pi x pi y. Now if you remember that if these were canonical momentum, then p x p y should be equal to 0, because the x component of p has got nothing to do with the y component, but they are not canonical, as we have said earlier. So we just say that they are not canonical because xi pi j, this is not equal to delta ij. What I mean is, I mean IH cross delta ij, if you like, IH cross delta ij, or just let me write it as delta ij and so on. Okay. Okay, you can write that, and then of course you have a pi I pi j is not equal to delta ij as well. Okay, so that's why they are not canonical. All right. So these are some of the features of this. Of course, as I said, that they are gauge invariant and so on. So one can actually prove the commutation relation as this pi I pi j plus EAI. So this and PJ plus EAJ. This is equal to minus E, and there is a del A del x I minus del A I, this AJ, and this is XJ, and this is equal to minus E epsilon IJK BK. I am writing in the tensor notation, but you do not have to, but you work it out. Remember that these Pi and Pj, these are canonical momenta, and then work out various things. You will get this. Okay. So if you put in there, then A dagger becomes equal to, so I over EBH cross multiplied by minus I EH cross B, and these will cancel and will give you equal to 1. Okay. So A dagger commutation is equal to 1, and these are important. Okay. Now in order to understand the degeneracy of the Landau levels, we are simply now playing with the Hamiltonian, various terms of the Hamiltonian, and writing them in terms of this pi x and pi y operators, and these are momentum operators. As I said, they are gauge invariant but non-canonical. Okay. And we can introduce another variable. So, introduce a pi tilde. This is of course a vector pi tilde. This is equal to a pi minus EA. Okay. The advantage with this, you will see in a moment, it has the other property that pi tilde is not gauge invariant, but canonical. Okay. So, we introduce this pi tilde operators and write them in terms of the pi operators, all right. And also it has to be kept in mind that the vector potential enjoys a gauge freedom, which we can write it as A minus grad chi, where chi is some scalar quantities, and the reason that such a thing exists because your curl of A has to give you a B. So, a curl of A prime should also give you a B, which is curl of A minus grad chi, chi being a scalar. So, let us write that. So, an arbitrary scalar, it can be any scalar. Okay. So, this is equal to curl of A and minus curl of grad chi, and this is equal to 0 simply for the reason that grad chi is a direction, it is a vector which has a particular direction. If you try to take a curl of it, that is whether it rotates or not, and of course does not rotate, and that is why it is equal to 0. So, a curl of A prime will give you a B, the magnetic field that you want, and as well as curl of A. So, and that is why you can write down A to be ambiguous by the amount A minus grad chi, chi being a scalar. Okay. And so, this will enable us to write a pi tilde prime, okay, which is equal to a P prime minus E A prime minus grad chi. Okay. That is what is there. If you lift the prime, then you can lift prime all throughout, and then you have to drop the grad chi as well. So, the important thing is that for these commutation relations of these quantities, okay, let me not write it with a vector anymore, we write it with just a tilde. So, x say for example, and pi y tilde prime is equal to I E H cross by B. Of course, this sort of differ from the commutation relations of pi x and pi y by just a sign, but there is an additional advantage because each of these pi I tilde and pi j prime tilde, this is equal to 0, which means that they are canonical. So, this primed momenta they are canonical, whereas the unprimed momenta, even though they are gauge invariant, they are not canonical. Okay. All right. So, this is our discussion so far, and so this is, it is good that it is equal to 0. So, if you want to write down the Hamiltonian in terms of these A and A dagger operator, then one can write it as it is a dagger A plus half. That is the form of the Hamiltonian. You can check that with the definitions of A and A dagger if you write them, and then you will get this. So, your Hamiltonian will become equal to, let me write it here. So, your Hamiltonian will be equal to, so this P x, or rather P plus EA whole square by 2m. Okay. So, this is the P changes to P plus EA and so on, and then of course, you write it in terms of pi, and then when you do that, then convert it into the A and A dagger, and this certainly gives you the the number density or the number operator corresponding to this problem. So, this is equal to nothing but equal to h cross omega b n plus half and n is equal to 0, 1, 2, which denote the indices of the Landau level. Okay. So, that is our Hamiltonian and written now in terms of the operator. So, it is n cross n operator, which is the number operator, and it is written in the Fock states. The problem, as we have already figured out, that if you do it in the symmetric gauge and when none of kx and ky are conserved quantities, it is difficult to see that where the degeneracy is coming from, because that is where in the Landau gauge we have gotten this degeneracy from the conserved quantities such as kx or ky depending on the gauge chosen. But here both are non-conserved quantities, and hence finding the degeneracy is a bit challenging, but then we know that what the solution is. The solution would be introducing the angular momentum operator, and in order to do that, let me introduce new set of operators. Okay, and the new set of operators are nothing but so this b, which is equal to 1 divided by 2 e h cross b, and pi x tilde plus I pi y tilde, that is your b, and the b dagger is of course the minus sign that goes inside the bracket. So, it is 2 e h cross b and a pi x tilde minus pi y tilde. Okay. So, these are the b and the b dagger operators, and you can check that b dagger is equal to 1. Okay. And these b and the b dagger will give degeneracy of the levels. Okay. So, that we will see how. So, now we of course have one quantum number. So, what are the quantum numbers that we have? So, we have of course n, which is which appears in the Hamiltonian, which is the eigenvalue of the n operator, the number operator, which acts on the Fock space, giving us the number of oscillators present in the problem. And the other one is m, which comes from, so this is included in the energy, and this is included in the angular momentum operator. And what I mean by angular momentum operator, such as if it is a z component of the angular momentum, then z is equal to, it is like r cross p and the z component of that, assuming that we are not talking about spin, otherwise this would just be Lz. Okay. So, our quantum numbers become, there are two quantum numbers which are n and m, and this should label uniquely the Landau levels or the wave functions corresponding to the Landau level. Okay. So, let us write these things as a ket comprising of these numbers. So, this is n and m. So, this is equal to a dagger n, a b dagger m, and this is divided by n factorial m factorial. So, this acting on the vacuum 0 0 will give us a Landau level starting from the vacuum. Okay. And of course, we know that a 0 0 is nothing but equal to 0, and as well b acting on 0 0 gives nothing but 0. Basically that you cannot lower these n and m indices any farther, that is why the A acting on 0 0 or the B acting on 0 0 will give you 0. Like A and B in their respective ways, they are the annihilation operator. You can't annihilate anything below 0, that is why these things give you 0. And what is the Hamiltonian for this? So, Hamiltonian is 1 over 2m, and we have a pi dot pi, that is the momentum, and this is nothing but equal to 1 over 2m p plus EA whole square. Okay. Now, we bring in all those non-canonical momentum, but that are gauge invariant in order to write H. You can also write it in terms of pi tilde, it really does not matter. Okay. We will have to construct the Landau level wave function. So, if you look at one slide before, 2 slides rather, you see this energy expression that you see, I mean, or the Hamiltonian is simply that of a harmonic oscillator. It is a simple harmonic oscillator, and even you can think about it in just one dimension, where n is just the quantum number, one single quantum number that can take values n equal to 0, 1 and 2. Okay. So, now we have to find the degeneracy and find the wave function. And in order to do that, let us write down again this A operators, which are 1 divided by, in terms of this pi over h E b. This can also be written as using h cross equal to h over 2 pi. So, we can write this down equal to 2 E h cross b pi x minus I pi y, and this is equal to 1 divided by root over 2 E h cross b, and this is equal to a p x minus I p y, and a plus E a x minus I a y. Okay. So, if you write down this pi x in terms of p x and a x, and pi y in terms of p y and a y. So, this is the thing. Now, what I will do is that I will introduce this p x equal to minus I h cross del del x. Okay. And then from there we will do something else. Let us see what we do from there. So, it is 2 E h cross b, and we have minus I h cross del del x minus I del del y plus E. Now, I will write A x and A y also in terms of b. So, it is E b by 2 and a minus y minus I x. Okay. This is quite important, because your A, that is the vector potential, the A x and the A y, they are position dependent quantities. Okay. In this case, it is very clear that they grow linearly with x and y, and because of this really the momentum becomes non-canonical because of these position dependent terms, and that is why it refuses to give rise to those canonical commutation relations that we are very familiar in quantum mechanics. Okay. So, this is the form of this A, and we can also write down A dagger and so on. So, we will use this quantities here that you see and you see here, we will use complex numbers for these quantities. So, we will use z is equal to x plus or x minus I y, and we use z tilde as x plus I y. You might wonder that why I am using the opposite definition, that is z is usually taken as x plus I y, and z tilde is taken as, or z star rather is taken as x minus I y, but here we have taken. So, z tilde is nothing but z star. Okay. Now, we are doing it for a purpose, that is z is taken in this particular fashion for a given reason, and let us also define a shorthand notation, that is half of del del x plus I del del y, which appear here as you see, which appear here, that is del del x minus I del del y, or del del x plus I del del y. This we write it as delta. Okay. So, this is delta, just a shorthand notation, and similarly we will use a half of del del x minus I del del y. This is equal to, so this is not 0, just to make sure, this is like this and this is like this. Okay. So, this del or del tilde is what these things are, and this is important to understand that del z is equal to del z tilde, this is or del tilde z tilde is equal to 1, because you see that if you take this del z, this is equal to half of del del x plus I del del y, and this is going to act on this z, which is x minus I y. And this will be half, del del x of x will be equal to 1 and del del x of I y will be 0, and I del del y will be of x will be 0 and del del y of that will be equal to 1, but then there is a minus I square. So, that will give you a 1 and this will give you a 1. Okay. Then that is why you can check for the other one as well. So, this del z, so this is an operator which is of the form that we have shown here. So, this acting on the z will give you 1 and so on. Okay. So, in fact, now these A and A dagger, so we will write A and A dagger in terms of the coordinates z. I mean, I am using this inside quotes because x and y are definitely coordinates. So, z is a coordinate which is a combination of x and y, but now in the complex plane, because it is x plus I y or x minus I y. Okay. So, A is equal to a minus I root 2 LB, that is a magnetic length that we have studied, plus a Z for LB. There is some specific way of writing in order to make sort of the notations simple, and this is LB tilde minus Z tilde, this is for LB. This will not be a tilde. Okay. All right. So, this is fine. Now, LB is equal to H cross over EB, root over H cross over EB, which is what we have studied earlier. It is basically the magnetic length and it is related to the guiding center, which we have discussed, this motion of the electrons in a magnetic field. Okay. So, these are some of the notations, some algebra. Algebra is very simple, just finding out commutation relations, etc. You can easily do that. So, this tells you that what we do is A acting on 0 m, that has to be equal to 0. Okay. So, we will start with a state which is starting with a wave function Nm. Okay. Just making sure that you understand what these Nm are. N is equal to the quantum number corresponding to the energy, and m is still what we are yet to find. It is the angular momentum quantum number corresponding to Jz or Lz. Okay. This is true because if n is equal to 0, then applying this annihilation operator would yield you 0. This is the usual property of the Fock state, that the state where there is no oscillator, you cannot reduce it any farther. So, this tells you, now I will put the form of I, and that tells you that this A is equal to LB delta plus Z and 4 LB and 0 m, that should be equal to 0. Okay. Now, that tells you Okay, so this makes sure that this is delta. So this operator acting on 0m ket would give you 0 because there is the n quantum number is equal to 0. So, you can't reduce it any further and so on. So, if you open this up and do a little bit of calculation. So, these 0m is let us call it as the L psi LLL and is a function of z and z tilde. LLL means lowest Landau level. Okay. So, if we take the lowest Landau level and then put m equal to 0 as well, then this has a form, unnormalized form is minus z mod square divided by 4 LB square. Okay. And this is nothing but it reminds you of the ground state wave function for the harmonic oscillator. So, this is the ground state corresponding to m equal to 0, there is no m here, and in terms of the coordinates this is written as exponential minus mod z square by 4 LB square. LB is what we said earlier, LB is equal to this, and this is just the Gaussian like this in the complex plane. So, this is so this is psi of z. So, this is a function of z and z tilde or z star, and this is at z equal to 0. So, this is of the form of a Gaussian. This is well known that the lowest wave function for the harmonic oscillator is just a Gaussian. As you go to larger and larger or rather excited states, you will have a polynomial coming in as a coefficient, and this polynomial has properties such as this corresponding to even n, it's an even polynomial, and corresponding to odd n we have an odd polynomial. Thankfully, we will be talking mostly about the lowest Landau level here, and then we should be happy with this Gaussian form that you see here. Okay. If you want to have an ansatz that what is it for LLL m not equal to 0 and is a function of z and z tilde, then it should be it's like a z over LB to the power m, that is a polynomial, and then z square divided by 4 LB square. Okay. So, this is the Gaussian multiplied by a polynomial and so on. Now, we will introduce the and just for our notation we will write it as Jz instead of Lz, but as I said that you can see Lz written in some books and notes. So, we just use the total quantum number notation J. So, this Jz is nothing but equal to H cross, which is of course the scale of the problem, and Z del and minus Z tilde del tilde. Okay. So, just to remind you that these are the definitions of delta and delta tilde. Okay. And this z is of course x minus iy and z tilde is x plus iy. I told you that this is not in the conventional form, but this is what suits us the best in terms of these the definitions that you know of z and z star or z tilde. Okay. So, this is the z that you have, and then of course, just to remind you that z is equal to x minus iy, z tilde equal to x plus iy, and delta is equal to half of del x plus I del y, half of del x plus I del y, and delta tilde is equal to half of del x minus I del y. Okay. These are the definitions, and this is that, and you can check that your Jz acting on these psi LLM, okay, even for m equal to 0, it gives you m h cross psi LLM, which is a known result even in say hydrogen atom problem. So, you put all these z and delta and then take this the form that you have, do not put the form of z, keep z as z and z tilde as same, and remember that your z mod square is nothing but equal to z tilde. Okay. So, when you take a derivative with respect to z, it will be left with a z tilde, and when you take a derivative with respect to z tilde, it will be left with a z. Okay. So, that is how. Okay. So, this is that relation that you have. So, m is the angular momentum quantum number. So, do not make a sort of confusion between m to be equal to mass and m to be equal to the angular momentum quantum number. If you feel that there is a problem, then you can write this m as mj. Okay. But if you feel it is fine, we know how to distinguish between them, then you can write it as m. Okay. So, we have taken a gauge which is symmetric, and in the symmetric gauge neither of kx and ky were constants, and we wrote down the Hamiltonian in that symmetric gauge, solved it and got a result which is identical to what we have gotten it with the Landau gauge for an electron in presence of a magnetic field. And it should be, because the result should not depend upon the gauge, because energy is a physical observable, or it is a measurable quantity that should not depend on the choice of the gauge, and which we have seen. And then we have gone ahead and calculated or rather introduced various quantities such as A and B, and wrote down H in terms of A and B, looked at the commutation relations of A and B in order to understand do they correspond to, and then finally use them in order to write down the Hamiltonian, and then Jz, and then Jz acting on this psi LLL will give me the lowest Landau level and corresponding to any m. So, m is the degeneracy. M equal to 0 correspond to the lowest Landau level, m equal to 1 will also correspond to. So, this value of m will get you the degeneracy that we have even in the case of Landau gauge, where the conserved quantities such as kx and ky gave us a Landau level degeneracy. Now, the Landau level degeneracy is given by this value of m or mj that you see. I will remove this j and just hope that you do not make a mistake between m to be the angular momentum quantum number and m to be the mass. Okay. So, you can write down h equal to 1 over 2m, this m to be the mass and not the m above, okay, the quantum number. All right. This is equal to p plus EA square and so on, and then I can write it down in terms of all these things. These are customary, but they are quite important too. So, it is 1 over 2 LB square, and this is equal to minus I del x minus y by 2 square plus minus I del y plus x by 2 square. This is the Hamiltonian, and if you use variables such as x minus iy, which is what we have done, and z tilde equal to or we can do a z star here, which is equal to x plus iy. So, z plus iy, and write down this as r e to the power I theta or minus I theta, and write this as r e to the power I theta plus I theta. So, z star and z tilde are identical. Okay, you can write it with whatever notation you want. So, the derivatives can be written as so a del x can be written as a del z plus a del z star, and a del y can be written as minus I del del z minus del z star. So, this is del x and del y. So, in terms of this z and z star, the Hamiltonian can be written as 1 by 2 LB square 1 over z 1 over 4 z square minus 4 del 2 del z star minus z del z plus z star del z star. Okay. And it's basically this has some similarities with the harmonic oscillator, but the similarity is not very well defined because of these mixed derivatives like z del z and z star del z, etc., etc. But these mixed derivatives are the main thing. Now we can use these same set of ladder operators that we had done earlier, which are b and b dagger. And so, this is equal to b equal to 1 by root 2 z star by 2 plus 2 of del z. This is your b, and your b dagger is equal to 1 by root 2 z over 2 minus 2 del z star. You can change all your z tilde to z star if you want. And this is a equal to 1 by root 2 z by 2 plus 2 del z star. Now, I am writing both the a and the b operators together, and your a dagger is equal to 1 by root 2 z star by 2 minus 2 del z. So, these are my a and b operators, and a and b operators have a similarity that both of them their commutation relations they obey equal to, the commutation relations obey equal to 1, and it can be written as so H is equal to a dagger a plus half. This is the Hamiltonian. Of course, your H cross omega, etc., they are absorbed in the definition because of these LB square being there. And the angular momentum so Jz is written as this is a usual definition that you know in terms of the, it's a derivative of only the phi. So, this is equal to minus H cross z del z minus z star del z star, and this is equal to a dagger a minus b dagger b. Okay. So, that is the form of this z, and the eigenvalues of z are minus they are minus mh cross, and m varies from minus n to plus n. Okay. So, this is quite important, that this is the degeneracy of the Landau levels. So, for each n it will vary like this. Okay. So, b will decrease m by 1 unit and b dagger will increase the m value by 1 unit, just like any of the ladder operators, whereas a dagger increases n by 1 unit and decreases n by 1 unit. So, b dagger increases m by 1 unit, b decreases m by 1 unit, a increases n by 1 unit, a dagger, a decreases n by 1 unit, and so on. So, these are the reasons that we have so far introduced them, and we have carefully dealt with them, and m goes from minus n to plus n. and so on. So, it is like that the harmonic oscillator problem now has two indices, and these two indices are the wave function have two So, for a given value of n, there are so many values of m possible between minus n to plus n, and then you go to another value of n, again from minus n to plus n, all these values are possible, and these n and m can be written as b dagger to the power n plus m divided by root over of n plus m factorial, and a dagger to the power n divided by root over n factorial, and so this is 0 0. Okay, just like we create the excited states in the harmonic oscillator by applying these A and A dagger, or rather we built excited states by applying A dagger successively once, twice, thrice and so on in order to get the first excited state, second excited state and third excited states. Here we get the different Landau levels, or the wave functions corresponding to the Landau levels by applying both the A and B operators in this particular fashion. Suppose you want to get to 1 1, in which case the n is equal to 1, in that case m has to become equal to 0, and then you can write down. So, 0 0 what we have written down earlier is a simple Gaussian. Now we are writing the normalization, which is equal to exponential minus z mod square by 4 lb square. Once again, just to remind you that this is equal to a z z star. Okay. Of course, these a 0 0 obeys equal to b 0 0, that obeys equal to 0. So, you cannot annihilate any further, and if you successively apply b dagger m times on 0 0, you will get a state which is 0 m, of course, because it builds up the m values, and this will give us a z to the power m exponential minus mod z square by 4 lb square, and this is the normalization is 2 pi 2 to the power m factorial. Okay. So, these are the properties of the Landau levels, and as I said that for a given m, you will have to have a polynomial which is z to the power m, there is a normalization constant that appears there and so on. So, each time you operate a b dagger on the 0 0 state, you get a z. So, you operate it twice, you get a z square and so on and so forth. Now, I will simply write down this nm state, which is a general Landau level, which is not of too much of relevance to us, but still for the sake of completeness, because we will be mostly talking about the lowest Landau level. This is just for an expression that you may keep it for record. So, it is 2 to the power 2 m plus n, and n factorial m plus n factorial, that is the normalization, and this is equal to a b dagger m plus n and exponential minus z mod square by 4 lb square. That is a general Landau level. Okay. This is the expression for a general Landau level and so on, and then you can write down this in terms of these z and z star and so on and so forth, and let me still write it once. So, that so this is 2 pi 2 to the power 2 m plus n, n factorial m plus n factorial, and a z star minus 2 del del z star to the power n z minus 2 del del z to the power m e to the power minus z square by 4 lb square. So these are the general Landau levels. So you want a particular Landau level, say n equal to say 3, m equal to 2, and so on and so forth. You can adjust that power accordingly, 3 and 2, and then take a derivative of the Gaussian term that you see on the right, and then find out the wave function corresponding to that value of n and m. We'll next talk about the properties of these Landau levels. These are in particular called as the Laughlin wave functions, which has been written down by Laughlin purely from an intuitive viewpoint, and some of the properties we'll talk about.